Alright, let's see if the microphone cuts out again like it did yesterday. Alright, so we are on page 20, integrams with infinite discontinuities. Alright, that's awesome. 12 seconds. It seems like it's working better. Alright. Integrams with infinite discontinuities. So the issue is, like, when you're trying to find the area under a curve, what if your bounds, what if you are wanting to find the area under like 1 over square root x? Well, at x equals 0, the issue is it's undefined. Alright, so 0 to 1 because it's undefined, right? 1 over 0 is undefined. That's an issue. We're trying to take an integral where literally at 0, I'm undefined. It goes into infinity. So first we find the area of the portion from a to 1, and then we find the limit as a approaches 0 from the positive side, and then that will be the area under the curve. So let's go step by step through this. So first we find the area of the portion from a to 1. So here, as long as a is greater than 0, we'll be okay. So ideally, let's see, another way to write this is going to be, let's see, the integral of x to the negative 1/2, because this is 1 over x, right? Dx. Do you see that? 1 over square root of x?
Yeah.
Well, this is the same thing as saying, let's see. Actually, we can just take the integral of this. This is fine. The integral of x to negative 1/2 is just x to the 1/2 over 1/2. That's the same thing as saying 2x to the 1/2. Okay. Can you see that?
Yeah, I'm just thinking really quickly.
Yeah, sorry. So you take the integral.
Yeah, okay, that makes sense.
Dividing by a fraction, same thing as multiplying by the reciprocal. Dividing by half, same thing as multiplying by 2. So this is equal to literally 2 square root x. So I'm evaluating that from a to 1. So that's going to be 2 square root 1 minus 2 square root a. It's also, you can say that's 2 minus 2 square root a. Okay, that's fine. And then let's take the limit as a approaches 0 from the positive side. So this is going to be the limit as a approaches 0 from the positive side of 2 minus 2 square root a. Are you okay? Okay, I started screencasting and it's actually working. The microphone isn't breaking, so you just missed like a minute. I want to get done with early because I'm keeping clock today at basketball.
Okay.
Do you have your notes? Do you want another packet? I have a practice test. I printed it for you.
I mean, I'll take
A day early. Printed it for you a day early. This is what we're going to go over tomorrow. Coming for Louis. I forgot he wasn't here. Also, Roman taught me a word. Beseder.
Beseder.
Yeah. He said something to me and I was like,
Beseder.
Alright. So the issue so far what you missed, the issue is, what if one of my bounds is, like, goes to infinity? I'm going from 0 to 1. I'm taking the area under the curve from 0 to 1 of 1 over square root x. But at 0, it's undefined because 1 over square root of 0 is 0. It is undefined. So what I'm doing is I'm taking a limit as a approaches 0 from the positive side. So I found from a to 1 the limit, and the integral. And now what I'm doing is as a approaches 0, what is this limit approaching? If I put in and as a approaches 0.
It would just be 2, yeah.
Why would you just do the integral from 0 to 1?
You can't because 0 is undefined for this function.
Oh, okay.
That's why.
But this doesn't have to do with improper integrals anymore.
It does.
How is that an improper?
Because we have a discontinuity.
Right.
Literally, when we have infinite stuff, it's going to infinity. Like, it's never gonna actually reach x equals 0. X equals 0 is undefined, so there's like a vertical asymptote there. But we're trying to find the area under the curve from 0 to 1. And so one of my bounds is like going to infinity. Okay. So the area under the curve from 0 to 1 is, therefore it's equal to 2. Boom, boom. All right. Let's keep going. I'll give you a second to think about it.
Got it.
Yay. How's your day going, Daniel?
Very tired.
Aw. Alright, improper integrals with infinite discontinuities. Whew. All right, so if f of x is continuous on a certain interval, then you can say the integral from a to b of a certain function is just going to be the limit as from c to b. Basically, you're just changing the bounds, and then you're saying, okay, as c is approaching a, it's basically exactly what I just went over. Instead of going from 0 to 1, I went from a to 1, but then I changed my a and I got closer and closer and closer and closer to 0 until I saw that I was approaching a certain limit. That's what's happening here. If it's continuous, then this is what we can do. If it's continuous, then we could do the other side. So instead of like at this top part here, just trying to find the integral right here, and this is where b was. So I kept moving my c over until I hit that certain mark that I was trying to get the integral of. The other one literally goes the other way. This is not like showing you very much. So I'm trying to approach this certain like a value over here. So you can take the integral here as like from a to b, and as my c gets closer and closer and closer to b, like I'm approaching this infinity. This is if you have like a discontinuity, either a removable discontinuity or a jump discontinuity or an infinite discontinuity. Maybe we're not going to infinity, like maybe we're not doing the end of the function going to infinity. Maybe I just want between maybe I just want between two numbers, like just an interval of it. Instead of taking the integral of like from 0 to infinity, maybe I just want, okay, so between like 2 and 4, what's the integral? Issue is, what if I have a discontinuity between those bounds? What if my bound isn't infinity, but inside there I have a discontinuity? What if it goes to infinity between my bounds? That's another way you can use improper integrals. And just a reminder, improper integrals literally mean one of your bounds is either 0, it is either infinity, or someplace goes to infinity. So improper integrals you can use to find the integrals at points that are discontinuous. Okay, so here in parts 1 and 2, what I talked about, the limit's finite, the improper, if we have a finite integral, then it converges, so we have a value. If the limit doesn't exist, we diverge. It literally, it doesn't like go to a number, it just like goes on, keeps growing. And then part 3, if we're trying to say, okay, from A to C and then C to B, this is literally like, oh, guess what? I have a hole in my function, and this is at A, this is at C, this is at B. If I can find the integral from A to C, and then I can find the integral from C to B, and if both of these are converging, then I know the total limit is converging. If only one of them converges, then I know that we have no value for the integral. It will diverge and have no value. It's kind of like what we were doing before. I think an example best states it. State why the integral is improper. So here I don't have infinity as my bounds, but something's happening. I'm not going to infinity. I'm not going to x equals infinity. But what is my y value at, for instance, 0? Oh, I'm sorry. Not x equals 0. Where is this undefined? Where is the bottom of my fraction equal 0?
1.
Yeah, so we have a vertical asymptote at x equals 1. Yeah, I just spent the last like 30 minutes rereading the whole chapter. To just to make sure, like, questions you guys have, so I don't doubt myself. Just making sure. Yeah.
Well, thank you.
So I'm a little bit space cadet right now. At x equals 1.
Yeah.
Are you just tired? Do you need coffee? Tea? Okay. So since we have vertical asymptote at x equals 1, that's literally where it's undefined. So I have a discontinuity at x equals 1, but everywhere else I'm continuous. Capiche?
Yeah.
What language is that word? I don't know either. So from 0 to 1, not including 1, in union 1 to 3, that's where I'm continuous, aka everywhere except where I actually have a discontinuity. So I have to break this down. So I'm going to have an integral from 0 to 1, and then I'm having an integral from 1 to 3. Yeah. I just don't want to include, I want to like cut it off. I just want to have this like slice. I'm like dividing into two different parts because I have this stupid discontinuity. Alright, so integral from 0 to 1 of dx over x minus 1 to the 2/3 plus the integral from 1 to 3 dx, let's see, x minus 1 2/3. So what we're going to do is say we're going to take a limit as a approaches 1 from, let's see, so this is 0 to 1. So as I get closer and closer to 1 from the left side, so I'm approaching it from the negative side, as a approaches 1 from the negative side of 0 to a, x minus 1 to the negative 2/3 power, dx plus the limit as a, do I use a? No, I use b, different letter. As b approaches 1, so I'm approaching 1 from the 3 side. So as I get closer and closer to 1 from the positive side. That's why I'm taking a limit at 1, because I don't want it to actually equal 1. Alright, from b to 3. X minus 1 to negative 2/3. Do you need a drink of water?
Good.
I just worry about you.
Yeah, no, good.
Okay. Alright.
I'm getting it too. It's just that's about all I can focus on right now.
That's fine. That's fine.
Yeah, I'm getting it
Okay.
now.
So, yeah, we're taking one-time limits because we're not approaching, since we have vertical asymptote at 1, from one of the sides we're going to go to infinity, from the other side we're going to negative infinity because that's a vertical asymptote. Alright, what is the integral of x minus 1 to the negative 2/3? Do we know what that is? I just want to make sure I'm not just like, blah, blah, blah. 3.
1 over x minus 1 to the 1/3 over.
Right.
Because it was on the bottom and now it'll be on top.
Yes.
Alright. Let me do this. From 0 to a plus, and then it's literally going to be the same thing. Limit as of b as it approaches 1 from the positive side. Of 3 x minus 1 to the 3rd from b to 3.
That's so weird how when it's just x to the 1 or anything to the 1, it goes to ln, but like
Oh, yeah.
and with this it just skips right over 0.
It
It's
flips to the
really
other side.
strange.
Versus if it was 1 over x, because if you subtract 1 from it, you're like, oh, x to the 0 is 1.
Yeah, exactly. It's really strange.
Yeah. I don't have a good, like, explanation of it. It's just, it's weird.
Oh yeah, no, it's just
Yeah.
strange, I know.
Let's see, so, let's input the bounds, and then we'll talk about as, why did that erase? As a approaches 1 from the negative side. Because I don't want to actually input 1. I just want to talk about what happens. I realized I shouldn't have done that yesterday. Like inputting, I do a lot of improper things. I'm like, oh yeah, let me input infinity, like 1 over infinity, like, oh, that's equal to 0, like, so that's very hand wavy. It's like, no. So, as it's approaching infinity, then this thing is approaching 0. Like, I need to make sure I'm being mathematically sound with you guys and not being lazy.
You're doing fine.
Meh. Thank you, though. All right, so 3, oh god, all right. A minus 1 to the 1/3 minus 3 to negative 1 to the 1/3. Yeah, let me just put in 0 minus 1. Ugh. 0 minus 1, and then I'll evaluate it later. Plus limit b as it approaches 1 from the positive side of 3 times 3 minus 1 to the 1/3 minus 3 times b minus 1 to the 1/3. Oof. Okay. So as we approach 1, this is approaching, let's see. As this approaches 1, this part is approaching 0. Make a different color. This part gets closer and closer to 0. So it gets closer and closer and closer to 0. This part, I mean, it's just like negative 3 times the cube root of negative 1, which is equal to what?
1. Oh, negative 1?
Yeah, the cube root of negative 1. Negative 1 times negative 1 times negative 1
-1.
is negative. Yeah, so it's negative 1. So this is minus 3 times negative 1 plus, let's see, this guy goes to, oh lord, 3 cube root of 2. And as b goes, because we're having b approach 1 from the positive, so at first this is like 2 minus 1 to the 1/3, and then it's 1.5 minus 1, and then we eventually get to like 1.0001 to the 1/3, and so this gets really, really small, and it approaches 0. So effectively, we have 3 plus 3, oops, I'm sorry, 3 plus 3 times the cube root of 2. That's what it approaches. So it converges. Because both sides of my, like both halves of my integrals, the first one approaches 3, the other one approaches 3 square root 2. I'm sorry, 3 cube root 2. And so therefore, we converge because both halves converge. Because both halves, both sides, both integrals converge. Awesome. Okay, 2 more pages. We got this. Do you want some chocolate? I have chocolate. Do you need sugar?
No.
I've never seen you this tired, even at 7 a.m.
Yeah.
I'm worried about you, okay? Do you need water?
No, I was just tired.
Okay.
It's not life-threatening. I'm not, no need to worry.
Okay. Alright, so...
Do you have any sleep last night? Yeah. Yeah, I'm just weird.
Oh, it's from last night?
No.
No.
I mean, like, I got a full 8 hours. I had a study period in the morning. I decided to call class. I'm just tired.
Do you need sugar?
No.
Okay. Let's do the next one. So, integral from 1 to 2 of dx of 1 over x minus 2 dx. So, we know that we have a vertical asymptote at x equals 2. Right? Because the bottom can't actually equal 2. But otherwise, this means I know that this is going to be continuous. If that's my point of discontinuity, then I know I'll be continuous at all other points, aka from 1 to 2. I'm including 1, not including 2. Do you remember interval notation? Blessed. All right. So, I don't have to break it up into 2 parts because it's like everything up until 2. So I'm going to do the limit as b approaches 2 from the negative side, because I'm coming from 1 to 2, so I'm getting closer to 2. All right, from 1 to b of, do I want to put this? Yeah, might as well. 1 over x minus 2 dx. So this will be equal to the limit as b approaches 2 from the left side of, let's see, this will be ln of the ln of x minus 2. Yeah, from 1 to b. Yeah. Sweet. This is equal to the limit as b approaches 2 from left side of ln of b minus 2 minus ln of 1 minus 2. So as b approaches 2, as we get closer and closer and closer to 2, the number inside here is getting smaller and smaller. It's getting closer and closer and closer to 0. Yeah? Okay. So as b approaches 2, what's happening to this term? Right? So we're getting closer and closer to having not ln of 0, but as we go from 1 to 2, like for instance, if I have 1.9, I'll be taking ln of 0.1. If I have ln of 1.99 minus 2, I'm taking ln of 0.01. Like what's happening as we approach, as b approaches 2, we're approaching ln of 0. What is the value of ln of 0?
1? No,
ln of 1 is 0. What's the... So
it doesn't exist.
like this is ln of x. So as we approach 0, right, so it's literally diverging. It diverges. Cool, that's it. QED, done.
That's the end of the lesson.
No. We still have page and a half. But that's the end of this problem. I'm just trying to make it clear, even so if you end up watching this later, you understand what we're doing. Alright, so when we cannot evaluate an improper integral directly, which is often the case, we first try to determine whether it converges or diverges. So sometimes you can kind of tell if it will diverge or converge. So if it diverges, that's the end of the story, you're done. But if it converges, you actually have to find the value. So this theorem of the comparison test, it's kind of like, remember how we always have to use other functions to figure out one that we don't know? Like remember the squeeze theorem or the sandwich theorem? How we like use other things that we know that are like bigger or smaller, and like if we can't find the exact value of the function we're interested in, but we know, okay, well, it's always going to be less than this other function, we can constrict it. And by constricting it, we're like, well, thus it has to converge, or thus it has to diverge, or something like that.
Right.
So that's the idea of the comparison test. So if f and g are continuous from a to infinity, with f always smaller than g, so, and for all x greater than a, so aka, this is like, if this is f.
I don't get the second part.
Which part?
Step 2.
Oh, okay.
Why if g of x diverges f.
So, okay, yep. So, oh god, don't die. Alright, so f is always smaller than g. Right? F is smaller than, like, g is always bigger. So if g is converging, it's like, bounding it in. So f will converge. If g of x diverges, then f of x also diverges.
But not necessarily. Because then f of x could just level out to 2 and g could go on to infinity.
Let's see. So basically what's happening is, okay, can I erase this little graph thing?
Yes.
Okay.
Yeah.
Yeah. So this first one, I want you to notice that this is the smaller one. If the smaller one converges, the smaller one will converge if the bigger one converges.
Right. That makes sense.
The bigger one will converge if the smaller one diverges. Sorry, if the bigger one will diverge if the smaller one diverges. Yes, they switched out the letters on you.
I see.
Yeah. If the bigger one converges, then you know the smaller one will converge. If the smaller one diverges, then you know the bigger one will diverge.
Right.
Yeah. Okay. Yeah. So. Yeah, so if you know the smaller one is diverging, cool, that must mean the bigger one is diverging as well. If the bigger one converges, then you know the smaller one has to converge. It's like if the one that's underneath goes to infinity, then the one that's always above it, because it's literally defined as always being bigger, it also has to go for, crazy. Okay, cool. So sorry, that took me a second. So let's use the comparison test to determine whether the integral converges or diverges. So this feels just like, what was it, the sandwich theorem, squeeze theorem, all these other ones. It's literally like, if we can bound it, between 0 and another function, then we're fine. So for instance, this one, if I can have, pick your color. All right. So if I go 0 is less than or equal to 1 over x cubed plus 3. I know that one is always smaller than what? What would be a good one to,
It's bigger than that, not smaller.
Let's see. Oh, yep. So we need to find one that's always bigger than this. So a function that's similar, but always bigger. What if I did like 1 over x to the third? This is always bigger than 1 over x to the third plus 1. Because since we're 1 over x to the third, for instance, if I put like 1 in, on the right side I'll have 1, on the left I'll have a half. What if I put 2 in for x? On the right side I'll have 1 over 8, on the left side I'll have 1 over 9. So it's always bigger. It's because we have that plus 1 and we're in the denominator, so we're always going to be just a little bit like smaller overall. The denominator will be like a bigger number, but the fraction itself will be smaller. Okay, cool. So, do we know, let's see, because this one would be hard to come up with. Do we know if 1 over x to the third converges or diverges? How do you know?
What?
How do you know?
Because as it goes to infinity, it goes closer to 0.
Yeah, so it converges. So thus, guess what? The middle one has to converge as well. So we can prove that. So since the limit as a approaches infinity from 1 to a, this is exactly, Danielle, you're fully correct. Let's see, x to the negative 3 dx. Since that's equal to the limit as a approaches infinity of, let's see, x to the second over 2. Yeah, x to the second over 2. X to the negative second over 2.
This is just you justifying that that's true.
Yeah, it's exactly what Daniel said, like how it goes to infinity. This is equal to the limit as a approaches infinity. Do I want to put it over? Yeah. 1 over 2a squared minus 1 over 2. So as a goes to infinity, the first term approaches 0. So this approaches 0, and then I just get, let's see, minus, did I forget a negative? I did.
No, I just think.
There's a negative right here.
Yeah, but I also think 2 goes on top, doesn't it? It's
Mm,
negative 2x to the power of negative 2.
like
Or
divide
you divide by. You're right.
Okay. So this turns into a positive 1/2. So it since 1 over x cubed, the integral of 1 over x cubed from 1 to infinity is 1/2. It converges. You know the middle one also converges. So therefore, we know the integral from 1 to infinity of 1 over x cubed plus 1 dx. We know it converges because it's like being bounded in by the other. All right, last page of notes. Holy bajoli, we got this.
How many problems?
Two problems. Yeah, we got this. All right, so and then tomorrow we'll do the practice test. Cool.
There's no discontinuity, right?
So there's not. There's no discontinuities. That's awesome. Let's see. So let me just. So this says no discontinuities because no matter what x I plug in, it'll always be positive, and I'll be fine. Okay. So let me use the theorem. So 0 is less than or equal to 1 over square root x to the 4th plus 1. Which is less than or equal to. Okay, if I didn't have this plus 1, what would the denominator be? If I didn't have that plus 1, could I simplify it?
Yeah, it would be x to the 4 or x to the 2.
Yeah. So is x 1 over x squared, is that always bigger than the one that's in the middle? Yeah. For instance, if I put 1 in for x, I would have 1 over square root of 2 versus 1 over 1. 1 over square root of 2 is smaller than 1. But if I put in 2, 2, 4, 16, 17. Yeah, 1 over square root of 17 versus 1 over 4. So it's definitely like 1 over root 17 is definitely smaller than 1 over 4. Yeah, because the root of 17 is definitely bigger than 4. Since we have a bigger denominator, the overall fraction is smaller. Okay, cool. Do we know if 1 over x squared converges?
Yes.
Yep. Where are we going from? Negative. Oh, ooh. We're going from negative infinity to infinity.
So we don't know about negative. Right?
So what about?
So we have to split it up into 2 integrals.
Yeah. We do.
Do we need to do that yet?
No, we have to do it right now. Sorry. I'm just thinking, I don't know. Did I think this through? Should I do on 0?
Can I get some water?
Yeah, it's fine. I feel like I should have. No, I can't have it equal 0. Okay, so it should be the limit as. Are you okay, Bradley?
Yeah.
Just fall asleep?
No,
Worst.
I did not.
Alright. As a approaches negative infinity, I'm trying to figure out why I put the bounds as a to 1 and then 1 to b. Why 1? Because what about 0? Oh. Because this one, okay, that's why. Bradley,
Yes,
you just fell asleep.
I did not. I hear everything you're saying.
Okay, the reason why I'm going to put my bounds from negative infinity to 1 and then from 1 to infinity is because, like, between negative 1 and 1, this is not going to be true. So that's because when you square, like, 0.5, the answer is a fourth, but when you cube 0.5, like it's going to be much, much smaller, and since this is on the bottom of a fraction, yeah.
Okay.
Anyway, so I only want my bounds to be where this is actually true, where my inequality is true, so that's why. Okay, I said that multiple times. Hopefully people, if you watch the video, you'll understand it.
I'm sorry, I don't think I fell asleep.
Huh?
But I just got tired.
It looked like you fell asleep. Your eyes were closed. You were breathing deep.
Or I was just being relaxed. One of the two.
Shoot. Okay.
Did we lose Daniel? Did he
He went to go get water. See, you were asleep.
Maybe.
Don't lie to me.
As soon as I realized that Daniel was gone, then I kind of thought maybe.
Okay, so the issue is I only can have bounds where this is actually going to be true. So, because remember, for all x greater than a, it has to be continuous from a to infinity. And it always, I only can be on the x's where my f of x is less than g of x, where my middle function is going to be less than my last function. So if I'm between -1 and 1, then this won't be true. That's the dealio. Because when you square a fraction, cool, the more times you square it and cube it and stuff, the smaller it gets. Well, guess what? If you made your fractions way, way smaller at the bottom, the overall fraction gets bigger. And then this whole inequality won't be true. That's why I did the bounds this way. All right, let's just evaluate. We're almost done. So this is equal to the limit as a approaches negative infinity of, let's see, -1/1 plus 1/a plus the limit as b approaches infinity of -1/b plus 1/1. So as a approaches negative infinity, that just approaches, so this approaches -1, the other one approaches, this guy approaches 0, the 1/a approaches 0, plus, let's see, as b approaches infinity, this approaches 0, this guy approaches 0, and then I'm adding 1, wait, -1 plus 1 is 0, dunzo. But it approaches a number. It's not approaching infinity or anything, right? So since x squared converges, we just proved it converges, we can say that, therefore, the integral from negative infinity to infinity of 1/x to the 4th plus 1, right, the square root, dx also converges because the other one converges as well. And the top guy was the one who bounded this one in. All right, last problem. Let's see if we can knock it out in like 4 minutes. Find the volume of the solid obtained by revolving the curve y equals x, eviate negative x, from 0 as less than x, less than infinity, about the x-axis. So, aka, this is my radius, this is my r. So I know the volume is going to be pi from 0 to infinity, because this is my bounds, of x e to the negative x dx. Oops, I need to square it because it's pi r squared. The x e to the negative x is my r, so that's why I'm squaring it. So my volume is equal to square root of the limit as a approaches infinity from 0 to a, x squared e to negative 2x dx. So I need to evaluate the integral of x squared e to the negative 2x. Try to think how you could do that. Hint, hint. Tabular method. Yeah. Tabular method.
Yay.
Whoop whoop. Alright.
I think they give us this much room on the actual test.
Give us this much room?
Yeah, for the problems.
Yeah, I need to double check.
Yeah.
I need to do that.
Because it's always nice when you have extra room.
Yeah. No. Alright, let's knock this out. Knock it out. Alright. Whew. Let's do some tabs. do some tabular method. There's this really cool thing in your book that's anyway, it's saying like even though the volume of an infinite solid can be finite, the shadow is infinite or something. You should totally look it up. It's interesting. Anyway, let's do some tabular method. Ugh, tabular method. All right.
You gotta either be happy or sad about it. You can't be both.
Yeah. So I have x squared, derivative 2x, derivative 2, derivative 0. Tubular dudes. Okay. And then this one is easy to derive. The other one's easy to integrate. So e to negative 2x is easy to integrate because the integration of that is negative 1/2 e to negative 2x. The integration of that is positive 1/4 e to negative 2x. The integration of that is negative 1/8 e to negative 2x. And then we just gotta, let's see, plus, minus, plus. Okay, now that we found the integral, let's go ahead and let's write it out. Volume is equal to pi times the limit. Honestly, the pi variable, the pi constant can be before or after limit. Limit as a approaches infinity of, oh my god, negative 1/2 x squared e to negative 2x. Oh, I gotta write a little smaller or it's not gonna fit. Minus, let's see, 1/4 times 2 is gonna be 2, so 1/2 x e to negative 2x plus, oh, it's just kidding, it's minus. 2 over 1/8 is, okay, so minus 1/4 e to the negative 2x from 0 to a. I have a, well, more or less I could make it all have a constant. Let's see, all of these have e to negative 2x. I could make them all have like a 4th factor in front. So what if I multiply this by 2 over 2, multiply this by 2 over 2.
Hey, what do you mean a 4th factor?
I'm sorry, a common factor. I just want to simplify this a little bit. I'm going to make it so I have over 4 e to the negative 2x. That's what I was just trying to do with that. So this would be negative 2x squared minus 2x minus 1.
Would it be 4 e to the 2x?
Where?
Right there. It's not negative.
Right, that's what I was fixing. Alright. Okay, so this is what I'm trying to evaluate from 0 to a. I know, that was nasty, so that's why I rewrote it. Pi limit as a approaches infinity. This is what the volume is equal to. Alright. Well, if I put in 0... Huh. Okay, now we can evaluate our limits. I'm sorry, our endpoints. And then I can do the limit. So let's see, this is equal to pi limit as a approaches infinity. Let me put in, let's see, negative 2a squared minus 2a minus 1 all over 4e to the 2a minus, let's see, minus, if I put in 0, everything goes away on the top except the minus 1. And the bottom goes to 4, so minus 1/4. Alright, as a goes to infinity, as a goes into infinity, the thing I care about is the a squared versus the e over e to the infinity. So what grows faster? A, like negative 2a squared, or 4e to the 2 infinity? Which one grows faster?
What?
I would like to know.
What you asked?
Huh?
What were you asking?
I'd like to know what happens to this term as a is approaching infinity.
So it would be,
AKA, what's growing faster? Does the a squared or the e to the a? Like, which one like really impacts me the
bottom
most?
grows much faster.
this type of thing. Right, the bomb grows faster, so this whole thing goes to 0. So this is going to be equal to pi times a fourth, aka pi over 4. That's it. End of lesson. I'll see you tomorrow.